All right, can everybody see the notes okay? All right, cool. Thank you. Appreciate that. All right, so we're going to build a polynomial with something called a monomial, which is something that I get when I go to the restaurant by myself. It's a monomial, so a single meal. Uh, a binomial would be a case where I go to a restaurant without any money. I buy no meal. But anyway, a monomial is an expression that involves an exponential expression. And it's going to look like this: a times x to the power of n. Right? Now, I want to mention a couple of things here. A is just going to be a real number. Okay, so something like 1, 2, 3, 4, or negative 1.5, things like that. And in this context, it's referred to as the coefficient. And in the context of monomials or polynomials, right, the n gets a special name as well. It's known as the degree. So that would be the degree of the monomial. And here are a few examples of monomials I can squeeze into here. You could have something like 2x cubed. Okay, that's of that format, a times x to the n. 2 would be the coefficient, and 3 would be the degree of the monomial. You could have something like negative 1/3 x to the 5th. Okay, negative 1/3 would be the coefficient, and 5 would be the degree. You can imagine that there are lots and lots of other monomials that we could think about coming up with. You could even have something like x, right? That's an example of a monomial because the coefficient would be that Secret Ninja 1, and the degree would be the other Secret Ninja 1. One more that I want to put up here is just a regular old number is an example of a monomial. So something like 5. Okay, that technically qualifies as a monomial because you could rewrite this as 5 times x to the power of 0. And we learned last time, or recalled last time, that anything to the power of 0 is 1. So in this context, 5 would serve as a coefficient, and 0 would serve as the degree of the monomial. And there are lots and lots of other monomials that we come up with. Yep, question?
I forgot to ask last class. I never had this explained to me. Why is it that x to the power of 0 or a number to the power of 0 is 1? Why is that?
Well, there's a couple of ways of showing that. I'll do it with the table. So let's say we had a table of x and y values, and let's say that we're getting our y values by taking 2 and raising it to our x value. This is an example of an exponential function, which is something that we'll do later on in the course.
Okay.
But I'm going to populate the table with some negative and positive values. So if we had like negative 3 going to positive 3 using the integers. So eventually we'll figure out by way of a pattern what 2 to the power of 0 is. And that would kind of be the reason why anything raised to the power of 0 is 1. And I'm going to start filling this table out actually with the x value of 1. If we took 2 and we raised it to the power of 1, that would give us 2. If we raised 2 to the power of 2, that would give us 4. 2 cubed would give us 8. And what we should see happening with the y values here is that to get from one y value to the next, we're multiplying by 2. So like if you multiply 2 to 2, you get 4. Multiply 4 by 2, you get 8. And the pattern would continue on. You could infer that the next y value would be 16. Now, if we wanted to work backwards, the pattern would be divide by 2. So like if I wanted to get from 16 to 8, one way of getting from 16 to 8 is to divide by 2. To get from 8 to 4, you divide by 2 again. To get from 4 to 2, you divide by 2 in the table. And then to get to this value, we do 2 divided by 2, which is what number?
1. Okay, thank you so much.
Yeah, no problem. Does that make sense?
Yeah, it does. Thank you.
No problem. The whole world has come together, right? With that little fact. There's like an algebraic way of showing that anything to the power of 0 is 1 as well. But that one involves some math acrobatics. I think the table is a little more intuitive and kind of a direct way of showing it. But yep, that'd be why anything to the power of 0 is 1. Okay, so a polynomial is going to be a sum, or difference really, of monomials. So what ends up happening to make a polynomial is you start combining 2 or more monomials together. And there's going to be another definition of a polynomial later, which is more symbolic in nature. For now, I'm just going to kind of keep it the intuitive stuff. But an example of a polynomial could be something basic like x plus 1. Each of those are monomials, so we're adding them together to form a sum, qualifies as a polynomial. And these things can get pretty large pretty fast. You're not really confined to how many terms or how many monomials that you can add together to create your polynomial. You could have something funky like negative x cubed plus 2x squared minus 5x plus 7. That would be an example of a polynomial. It has 4 monomials. We would also say it has 4 terms. All right. And I want to point out how I wrote this. I wrote each of the terms so that the highest power goes first, then the second highest power goes second, and so on and so forth. In other words, the degree of each of these monomials is decreasing as we go from left to right. And when we write a polynomial in this way, it's said to be in standard form. Okay, so standard form just basically means that you rewrite your polynomial so that the power is going decreasing order. So with that said, if I had something like 1/2 x minus 2x cubed plus 3x to the 4th, okay, that would not be in standard form because we're starting out with the smallest power in this case and increasing it from left to right. It's still a polynomial, but it's not in standard form. We'd have to do some switching around of the terms in order to have it in standard form. And there are definitely a lot of polynomials that you could, possibly come up with. So it gets, they get pretty crazy pretty fast. But with polynomials defined, it is possible to add, subtract, and multiply them. And next week we're going to look at the operation of division because that gets separate, and that gets its own separate section because it's a little more detailed than the other operations. So with that, I'd like us to start combining polynomials via those 3 operations. And we're going to start with addition. In example part A, we've got 2 times a polynomial with 3 terms, x cubed plus 3x squared plus 2, being added to 5 times another polynomial, x squared minus 4x plus 4. The overall operation here is addition. And notice that we have numbers in front of parentheses here. One thing that we want to do is clear parentheses, and we can do that by distributing the numbers that are in front of parentheses to all the terms that are inside the parentheses. So we do that first. 2 times x cubed is 2x cubed. 2 times 3x squared, 6x squared, plus 4. To that, we're going to add 5 times x squared is 5x squared. 5 times negative 4x is negative 20x. And then 5 times 4 is 20. Typically what happens is after you clear parentheses, there might be some like terms. So you want to combine those, and if you want to knock two things out with one stone, we can write our final answer in standard form as we combine like terms. So let's start with 2x cubed. All right, is 2x cubed going to combine with anything else in this line of math? No. All right, and x cubed happens to be the largest power of x that occurs here. So in terms of standard form, we would want to write that one out first. And I'm going to cross it off so that we don't try to combine it again with anything else. So now we have 6x squared. Is there anything that 6x squared would combine with in this expression? Yep, 6x squared is going to combine with 5x squared. So if you take 6x squared and add 5x squareds to it, you're going to get 11x squareds. I'll cross those off so we don't accidentally use them again. Now we have 4, which would combine with 20, but I'm not going to add those two together just yet because I'm also seeing this negative 20x, which according to standard form, we would have to write that next. And then we can combine the 4 and the 20 to get positive 24. And that would be our final answer. Any questions about that? All right, so with part B, the overall operation here is subtraction. There is a number in front of the second set of parentheses, it's 2, but to make things easier, you can treat that as a negative 2. And one way of using this negative 2 is to clear parentheses via distribution to all the terms inside of that set of parentheses. There's really nothing to distribute in front of the first set of parentheses, so we can just remove them, which is what I'll do in this next line of math. And if we distribute the negative 2, we'll have to do negative 2 times 3x squared, gives us negative 6x squared. Negative 2 times x is negative 2x, and then negative 2 times 5 is negative 10. So I'll give you folks a moment to combine like terms and write the answer in standard form, and I'll check in with you in just a few seconds. All right, let's see how we did. X cubed doesn't combine with anything. There is an x squared term, negative 6x squared, which doesn't combine with anything, but it will be written next. We can combine negative 3x with negative 2x to get negative 5x. And then negative 4 with negative 10 to get negative 14. So how does x cubed minus 6x squared minus 5x minus 14 look to you folks? All right.
Good.
Sweet, thank you. So the rest of the examples for the section of notes involve multiplication, a variety of multiplication types. In part C, I like to call this a direct distribution type of multiplication problem, because really all there is that you could do with something like this is just distribute to clear parentheses. And if there's anything that simplifies, simplify it. and then make sure your answer's in standard form and you're good. So basically, to handle something like part C, we're going to distribute 4x cubed to each of those three terms. Do you guys hear my dog barking in the background, just by chance? Sorry about that, guys. She's a corgi. She loves barking. So I'll get us set up with this one, and then I'll see if I can quiet her down. So what I'm going to do is take 4x cubed and multiply it to x cubed. It's the first term in the set of parentheses. And then I'll add 4x cubed times negative 5x. And then to that I'll add 4x cubed times 2. So while I go try to calm Toast, my corgi, down, if you guys could go ahead and multiply all three of these products together, and I should be back in time to go over the rest of the problem. All right, so sorry about that. I'll be right back. All right, neighborhood watch is calmed down. So I'm going to go ahead and multiply 4x cubed with x cubed. All right, we can multiply x cubed with x cubed. That's going to give us x to the sixth, right? Anytime we multiply two things with the same base, we add the powers together. So it's going to be 4x to the sixth. To that, we'll add the product of 4x cubed times negative 5x. Multiply the 4 and the negative 5 together to get negative 20. And then multiply x cubed to x to get x to the fourth. And to that, we'll add the product of 4x cubed times 2. Multiply the 4 and the 2 together to get 8. X cubed. One more thing that you could do here is just rewrite the addition of negative 20x to the fourth as just direct subtraction. So 4x to the sixth minus 20x to the fourth plus 8x cubed. And how does that look to you guys? So far, so good? All right. Any ideas as to how we could handle something like part D? It's another F word. Foil. You got it. Like that SpongeBob meme. Foil it. Foil it. So FOIL is really just like 2 rounds of distribution. Here's what I mean. You can consider 2x as something that you would need to distribute to clear parentheses with 4x plus 5. And you can also consider negative 3 as something that you would have to distribute to 4x and 5. And all those little arrows there help to make up the acronym FOIL. So for instance, when we first multiply 2x to 4x, it's as if you're multiplying the first term from each set of parentheses together, hence the letter F for that. Then we add 2x times 5. That would represent the O part. Since visually speaking, 2x and 5 are kind of like on the outside. They're like the outside terms of the expression. And then to that we'll add negative 3 times 4x. That would be the I part of FOIL. since negative 3 and 4x, visually speaking, are kind of like the inside terms. And to that, we'll add negative 3 times 5, which represents the L part of FOIL, since negative 3 and 5 are the last term in each set of parentheses. All right, so I'm going to have you folks take a moment to form all these products and then combine any like terms. Then we'll go over the answer in just a moment. Yep, go ahead with your question.
Sorry, what does the FOIL stand for?
The F part stands for multiplying the first term in each set of parentheses. So the first term in the first set is 2x, and the first term in the second set of parentheses is 4x.
Why is it an F then?
F stands for first. So
first.
like,
Then what would the O be?
The O is the outer. So like 2x and 5 are kind of like the outer
Okay.
terms of the expression. And then the I part would be for the inner terms, like negative 3 and 4x.
Okay. I see.
Yeah. Yep.
Okay, thank you.
No problem. Okay. So I'll go ahead and jot down my details so you can check yours against mine. A couple of like terms that you can combine after that. (8x squared minus 2x minus 15). How did we do? Survey says, good answer, right? Like on the Family Feud. Okay, a couple more examples and we'll be done with this section. For part E, the reason why this is a multiplication type problem is because of the power of 2. Okay, remember exponents tell you how many copies of the base you're multiplying together. In other words, it's repeated multiplication. Now, with 3x minus 5y squared, we could rewrite this as 3x minus 5y times itself. So anytime I see a power of 2, I just like to indicate FOIL, because when you write out 2 copies of the base, it basically looks like a FOIL problem, and that's how you want to handle it. Okay, so can I give you guys a couple minutes to work on that? And then we'll go over the results when time is up. So go ahead and FOIL these 2 expressions together, combine your like terms, and we'll go over the details in just a couple moments. Okay. So let's go ahead and FOIL. 3x times 3x, 3 times 3 is 9, x times x is x squared. Then we have 3x times negative 5y, so multiply 3 and negative 5 for negative 15. And then x times y, best you can do is just write that as xy. Then we'll distribute negative 5y. Okay, so don't forget there's a negative there. So that's going to be negative 15xy, you can write that as. And then negative 5 times negative 5 is positive 25. And don't forget the two y's multiplying together will give you y squared. You can combine like terms with the two middle terms, give you negative 30xy plus 25y squared. Now I'm definitely happy to just leave this as our final answer. You can kind of reorder things if you want so that it's 9x squared plus 25y squared minus 30xy. All right, both answers are definitely acceptable to me. I'm just leaving mine like this because to me it's as if the x's just start transitioning to the y's. But really there's no you know, hard rule as to how you want to write something like this. But that's it. How'd you guys do? Okay. Yep. Oh, it's awesome. All right. Part F is really just going to be handled much like a FOIL problem, except there's this additional term inside the second set of parentheses. But you know, we just handle this business as usual. We're going to distribute the x to all three of these. Then we'll come back around and distribute the negative 2. So x times 4x squared would be 4x cubed plus 3x squared plus 5x. You can come back around with the negative 2. We'll have negative 8x squared minus 6x minus 10. Combining like terms. Well, 4x cubed doesn't have anything to combine with. 3x squared does, though. Negative 8x squared. So 3 minus 8 is negative 5, which is why I'm writing this as negative 5x squared. Then we have 5x minus 6x to minus 1x, which I'll write as minus x. And then, of course, minus 10, which we'll just copy back down. And that is our 2-day polynomial basics. Any questions about what we went over so far?